This video will illustrate that the math behind creating chi-square tables is the same math we used when computing basic probabilities. We're going to do this by exploring two different events, but instead of events that we think might be dependent, we're going to choose two events that we know are independent because it shows the math more easily. Those two events are flipping a coin and rolling a die. So we know that an outcome of the probability of getting a certain outcome of a coin is 1/2, and the probability of getting one outcome on a die is 1/6. We also know that the probability of getting, let's say, a head and a 6 is the product of these two probabilities, or 1/12. Now let's connect this to a chi-square table. So we look at the table for flipping a coin and rolling a die. We see that knowing that these are two independent events, the probability of landing in any one of these squares is 1/12. Now, if we run one of these experiments where we flip a coin and roll a die 12 times, intuitively we can expect that we would get a frequency of 1 in each panel. Next, I want to go through these tables and show that the math we've been doing is really just the same math as simple probability. Intuitively, if we start with a single occurrence in each panel, we just go through a procedure, we add up the rows and the columns, and then to compute, say, this first panel in the lower table, we just do 1/12 times 6 times 2, which again equals 1. So we'd expect obviously the panels to be the same, but I just want to show you that this is the exact same calculation that we did before, 1/12 times 12. This process is just multiplying the probability of getting a certain outcome by the number of experiments you do. Now let's look at this. Instead of doing 12 experiments, let's say we do 48. Again, it's the same thing, multiplying the probability of getting in a given panel times the number of experiments you do. So in this case, it's 4. Now, we can rewrite 48 as 4 times 12, which is kind of interesting because this is like saying, oh, how many events go in each one of these 12 panels? So for instance, if we did 72, we could write that as 6 times 12, which would give us 6 in each panel. And so there's a pattern there where you can say the probability, the frequency is 1/12 times x times 12, and that gives you the kind of frequency that we would intuitively expect to be in each one of these 12 panels. Again, this number could be an integer, it could be non-integer, it could be kind of whatever positive number we want. So now again, let's do the same thing we did earlier where we're looking at this intuitive table, but let's go back to the case of 48 where we know that we expect there to be 4 occurrences in each panel, right? So we just really writing that as 4 times 1 in each case, and again we're doing this just so we can see the math. Do this across the rows and the columns, and then go to creating our sort of expected frequency. Going through our procedure, we get 1/4 times 12 times 4 times 6 times 4 times 2. Doing a little math where we eliminate 2 of the 4's, and we just simply switch a 6 and a 4. We get this formula, 1/12 times 4 times 6 times 2, which is really 1/12 times 4 times 12. Right? So this is what we get going through the chi-squared calculation. But if you remember, this is the exact same formula we used when we just did our straightforward probability calculation. So hopefully this illustrates that there's no magic happening here.